When the AI boom hit, billions of dollars poured into a brand new category of infrastructure, dedicated vector databases. Pinecone, Qdrant, Milvus, Weaviate. The pitch was everywhere. Traditional relational databases simply couldn't handle the high-dimensional math that large language models need, so you had to buy something purpose-built. But a quiet, counter-revolution has been happening. The two databases that have run the internet for the last 30 years, PostgreSQL and SQLite, both grew vector search extensions. And here's the uncomfortable truth. For the vast majority of production use cases, they are making specialized vector databases unnecessary. Look at this query. That little arrow operator is cosine distance. This is a full nearest neighbor search, ranking rows by how close their embeddings are to your query, running inside the same Postgres you already use for everything else. No new server, no new database to operate. This is really a story about data gravity, the simple idea that it's far easier to move your computation to your data than to drag your data across the network to some other system. So let's pull apart pgvector and sqlite-vec, expose the hidden tax of running a separate vector store, and get you the exact decision matrix for your AI app's memory layer. Start with the problem the dedicated databases create. On the left is what you sign up for, your application writing to two separate systems, your relational database for metadata, and a specialized store like Pinecone for the vectors. On the right is the alternative, one unified database where the metadata and the vectors live side by side. Here's why two systems hurt. When a user updates a document, your app fires two writes across the network. If Postgres commits the delete but the write to the vector store times out, your primary data says the document is gone, while your search index still thinks it exists. You've just lost transactional consistency. The two systems now disagree about reality. And cleaning that up is its own project. Reconciliation queues, retry logic, and background jobs whose only purpose is to chase down orphaned vectors and stale rows. That's real engineering time spent not on your product, but on babysitting the gap between two databases. This is where pgvector comes in. It adds a native vector data type and distance operators directly to Postgres. Because it runs in process, your embeddings and your metadata live in the very same table, under the very same transaction. If a transaction rolls back, both the row and its vector roll back together. You get full ACID compliance for free. And because it is just Postgres, you get the relational superpower back. You can filter your vector search by tenant, by status, by date, joining against your other tables in a single query. The specialized vector databases struggle with exactly this kind of metadata filtering. Here it is, just a where clause. For raw speed, pgvector builds an HNSW index, a multi-layered graph of your vectors. A query enters at the sparse top layer and takes huge jumps across the space, then drops down layer by layer, refining locally until it lands on the true nearest neighbors. There's also a lighter IVF flat index that partitions the space into lists and only searches the closest ones. The payoff is that pgvector can search millions of vectors in under 5 milliseconds, fast enough to sit directly in the path of a live request, with none of the synchronization risk of a second database. But what if you don't want to run a database server at all? You're building a desktop app, a mobile app, or an edge tool that has to work offline. That's where sqlite-vec by Alex Garcia comes in. It's a tiny dependency-free extension written in pure C, and it stores your vectors right inside a local .db file on disk. Now, sqlite-vec makes a deliberately radical choice. It has no HNSW, no IVF flat, no approximate index at all. It just does a brute force linear scan over every vector. That sounds slow, until you see how it scans. It leans entirely on hardware SIMD instructions, AVX 512 on Intel and AMD chips, Neon on ARM, to compute vector distances dozens of lanes at a time, right down at the middle. For datasets under 100,000 vectors, that hardware-accelerated scan is often under 10 milliseconds, with zero index to build, tune, or keep warm. So let's actually look at the numbers across scale. Under 100,000 vectors, sqlite-vec gives you sub-10 millisecond queries with literally zero infrastructure, just a file. Between 1 and 50 million vectors, pgvector with an HNSW index answers in under 5 milliseconds, matching or beating the specialized databases once you account for metadata filtering. It's only when you push past 50 to 100 million vectors, or when you genuinely need to shard horizontally across multiple regions, that dedicated databases like Pinecone or Qdrant become architecturally necessary. For almost every other application, the operational simplicity of keeping vectors in your primary database outweighs any specialized indexing advantage. So here's the decision matrix you can actually use. Is your dataset under 500,000 vectors? Use sqlite-vec, zero server setup, perfect for edge and local apps. Under 50 million, and you want relational joins? Use pgvector, full ACID. Only beyond 100 million vectors, and needing to shard, do you reach for a dedicated vector database. Because the lesson here is a classic system architecture rule, and it long predates the AI hype. Data gravity always wins. Moving your compute to your data is far simpler and far safer than syncing your data across different network hosts and praying they stay consistent. So before you spin up a dedicated cluster for vector search, stop and audit your actual scale. There's a very good chance you don't need a new piece of infrastructure at all. You might only need a few lines of SQL,